Let's imagine you were to dig a really deep hole, one that went straight through the Earth and out the other side. At the surface you will have a lot of gravitational potential energy, which will be converted into kinetic energy as you fall through your hole. That kinetic energy will be converted back into GPE as you continue to the other side. This is analogous to a pendulum, where by conservation of energy you must end up back at the surface of the Earth again by the time you stop moving. This is the notion of the gravity train, a theoretical fuelless method of transportation. Okay, time to do some math. Newton's law of gravitation states that the gravitational force of attraction between two particles is proportional to the product of their masses and inversely proportional to the square of the distance between them. The key thing to note here is the word particles. We cannot use this equation if we are studying the motion of objects that cannot be modelled as point masses. In these situations, Newton's shell theorems can sometimes be of use. The first theorem states that a spherically symmetric object affects other objects gravitationally as if all of its mass were concentrated at its centre. This is only true if you are outside the object. Instead of calculating the forces for every single particle, we can instead pretend that the object is a black hole. The second theorem states that the net gravitational force inside of a hollow sphere will be zero. For a particle at the centre, this is easy to see as any force exerted by one particle in the shell will be cancelled by the particle on the other side. For particles not at the centre, we can divide the forces into two groups. There are fewer forces that pull the particle away from the centre, as there are fewer particles, but each force will be stronger as the distance between the shell and the test particles are shorter. There are more forces that pull the particle towards the centre, as there are more particles, but each force will be weaker as the distances between the shell and the test particles are greater. These forces will balance and there will be no net force. Now that we can understand this conceptually, it's time to derive it mathematically. Consider a hollow spherically symmetric sphere containing a test particle at an arbitrary point. We can orient the sphere in such a way that the test particle lies along the border of two hemispheres. I could have just as easily drawn the test particle here, and due to the symmetry of the sphere, we can divide the two hemispheres in this way instead. This can be done for any point in the sphere. These two hemispheres will have exactly the same amount of mass, with each particle having a mirror image of itself reflected across the great circle. Each pair of mirrored particles will be equidistant from the test particle, so their forces perpendicular to the plane will exactly cancel, whilst forces parallel to the plane will add. This means we can focus entirely on forces parallel to the surface of the great circle bordering the two hemispheres. We can further divide this circle into two semicircles, and using the same logic as before, we can also ignore any components of forces that are perpendicular to the line connecting the test particle to the centre. This means we only have to consider components of forces parallel to the line connecting the test particle to the centre. In other words, due to the symmetry of the system, we can narrow down a three-dimensional problem to a one-dimensional problem, as the only variable that will affect the gravitational force of the test particle will be its distance from the centre. Let the test particle be located at point P, and let Q be a ring of points on the shell that are all equidistant from P. This means that the horizontal forces for each particle on Q are all equal. We can therefore model Q as a particle located at distance s from P, meaning we can use Newton's law of gravitation, where the denominator will be s squared. Big M will be equal to the mass of Q, which, assuming uniform density, will be proportional to the volume of Q. The density of the shell will be the mass divided by its surface area, which we can approximate as its volume as the shell is of infinitesimal thickness. We can further annotate our diagram to introduce r, the radius of the ring, and theta, the angle the distance s makes with the horizontal. Remember, the diagram is of a sphere, not a circle, so theta will be a constant for all points on Q. The width of the ring will be represented by ds, and the angle between the lines connecting either side of the ring to P will be represented by d theta. We can use the density of the shell, ρ, the radius of Q, r, and the width of Q, ds, in order to find the mass of Q. Mass will be equal to the density times the circumference of Q, 2 pi r, multiplied by ds. If we substitute m with this new expression, we get f equals minus gm 2 pi rho r ds over s squared. Remember, we only care about the horizontal direction, which is where our theta comes in. We simply multiply the force by cos of theta to get the net force exerted by Q on P. Now all we have to do is put everything in terms of one variable, then integrate to find the total force exerted by the sphere. Rho is a constant, so we only need to worry about r, ds, s, and theta. We can see that sine theta equals r over s, so r equals s sine theta. And for ds, we can use the cosine rule, where ds squared will equal s squared plus s squared minus 2s squared cos d theta. We can factor out 2s squared, then use the small angle approximation for cos to re-express cos d theta as 1 minus half theta squared. ds squared will therefore cancel down to s squared d theta squared, so ds equals s d theta. We now have three equations, our main Newtonian gravity equation, and two others for r and ds. If we sub these into the main equation, we get df equals minus 2 pi g rho s sine theta s d theta over s squared times cos theta. We can conveniently cancel the s's, as we have s squared in both the numerator and the denominator. We are now in a position to integrate, as remember df is only the force for one ring. In order to find the force for all the rings, we integrate with respect to theta. Our limits will be 0 and pi. Once we have set up our integral, we can factor out our constants, and as cos is the differential of sine, we can integrate by recognition to get a half sine squared theta. Sine of pi and 0 are both 0, 0 minus 0 is 0, and 0 times anything is 0, so our net force is 0. So what? Well, this means that we don't have to worry about forces exerted by matter our train has already passed, as we can treat the inside of the Earth as being made up of concentric shells, like an onion, which using Newton's second shell theorem, we know the net force from these would be 0, so we can just ignore it. Further, the first theorem tells us that we can treat the matter we have yet to pass as a particle, so we can use Newton's law of gravitation again. Big M will be the density times volume, which we can sub into our main equation, and then cancel the r squareds. Our new equation will now be proportional to r, again assuming uniform density, and we can use F equals ma to get an expression for the acceleration of the train as a function of its distance from the center. We can see that acceleration is directly proportional to the displacement from the equilibrium position, or r, and acts in the opposite direction, and this is the definition of simple harmonic motion. We can therefore use our SHM equations to find the time taken for the journey. Omega squared will be equal to 4 over 3 g rho pi, where omega squared is equal to 2 pi over the time period, and rho is the mass of Earth divided by its volume. We can sub in true values for the mass and volume of the Earth in terms of its radius, then cancel the 4 over 3's and pi's. If we churn through the math and rearrange for t, we get a period of roughly 84 minutes, giving us a journey time of 42 minutes, which is pretty good. But there are still some issues that we need to look into, the most important of these being extreme temperatures and pressures. The center of the Earth is 6,000 degrees Kelvin, and has a pressure of 330 gigapascals, which is over 3 million times atmospheric pressure. Given these wildly hostile conditions, even if we were able to manufacture a train to withstand the extreme temperatures and pressures, technology that we have yet to procure, it will also need to keep its passengers alive throughout the entirety of the 42-minute duration of the journey. Further issues include air resistance, which would result in the train having an insufficient amount of kinetic energy at the center to convert back into the necessary GP at the surface. Overall, gravity trains are a cool concept, but the sheer scale of the plethora of issues associated with actually building them, in addition to all the infrastructure necessary for their use, renders them at the very least extremely impractical, although more likely downright impossible. It would seem that, at least for the time being, conventional transportation methods prevail, but we never know what the future may bring.